Los Angeles, Wednesday, October 7th. Sunny today. Look for downtown highs near 80. KFI News Time now 6:34. Let's check the morning traffic again with Russ Carlton. Morning, Russ.
Good morning, Lubbock and Barclay, and we have an excellent commute on our hands so far this Wednesday morning. We have a disabled vehicle, however, blocking one of the traffic lanes northbound Santa Ana Freeway just north of the 605, and in the West LA area, San Diego Freeway southbound. A disabled vehicle, but it should be off the driving surface. With traffic, Russ Carlton, KFI.
Early morning in one of the largest cities in the world. Over 10 million people live in the greater Los Angeles area, and most of them have to travel long distances to work. Ask anyone what's so attractive about living in Southern California, and they'll tell you it's the sun. But the combination of bright sunlight with car exhaust fumes creates a problem for which Los Angeles is notorious: photochemical smog.
At the moment it's 8 o'clock in the morning. The freeways are already busy with commuters on their way to work. It's a beautiful sunny day and the air is clear, but the chances are it's not going to stay that way.
By using time-lapse photography, we can follow what happens on a typical summer's day. The camera is looking west, across the basin towards central Los Angeles. By mid-morning, the early mist gives way to a thicker cloud of photochemical smog. Normally, on hot sunny days, the air is warmest near the ground, and convection ensures efficient mixing. But what often happens in the Los Angeles basin is that a layer of cooler, denser air from the ocean moves in beneath the warm air. This is known as a temperature inversion and acts like a lid which traps the pollutants. The problem is made worse in Los Angeles because the basin is surrounded on three sides by mountains, which confine the pollutants even more. By midday, the prevailing onshore wind begins to blow the pollutants inland, towards the camera. As a result, the smog tends to be worst during the late afternoon, in the valleys that form the northern and eastern parts of the basin. It's these areas that feature most frequently in broadcast warnings, warnings that the residents take very seriously.
L&B, this is going to be one of those days as far as the smog is concerned. We a little earlier said that there were several first-stage smog alerts being predicted. We now have two of those, one of them here in the LA metropolitan area, the other one in the San Fernando Valley. And of course that means that those of you who have respiratory problems should stay inside, kind of curtail that activity, and if you don't have to drive, please stay off the streets.
Smog is a mixture of a great many components. Primary pollutants, such as hydrocarbons and oxides of nitrogen, secondary pollutants, such as ozone, and a great variety of solid particles. But how are they all produced? This tube contains nitric oxide, NO. Nitric oxide is produced in any combustion process. Watch what happens when I open it to the atmosphere. The brown gas produced is nitrogen dioxide, NO2, and it's pretty unpleasant. At the concentrations present in the atmosphere, this conversion doesn't usually go quite so directly. But the production of NO2 is a crucial step in the formation of another pollutant, ozone. This flask contains a mixture of air and ozone. It looks pretty harmless, but watch this. An ordinary rubber band, the ozone attacks the rubber because it's a powerful oxidizing agent. That's one of the reasons why it's so toxic. It's also an important factor in the formation of smog particles. Here's another flask with ozone. but this time, some lemon peel. That's called gas-to-particle conversion. The smoke is formed by the ozone reacting with the natural oils in the lemon peel. In the same way, ozone reacts with unburnt hydrocarbons from car exhausts in the atmosphere to form smog. But where does the ozone come from in the first place? It's formed photochemically, and that is where the light comes in. Sunlight is necessary to drive two of the key reactions that produce smog. In the first step, nitric oxide, NO, from car exhausts is oxidized in a fast, complex chain reaction that involves sunlight to produce nitrogen dioxide, NO2. The NO2 is then broken down by sunlight and reverts to NO plus a free oxygen atom. The NO can then be reoxidized to NO2, and so the whole cycle can be repeated. The combination of NO and NO2 is often referred to as NOx, or NOx. The oxygen atom, released by the photolysis of NO2, then combines with a molecule of oxygen to produce ozone, O3. Finally, the ozone reacts with the unburnt hydrocarbons released from car exhausts to produce a wide range of oxidized products. Some of these are present as particles, which gives smog its characteristic brown color. At the University of California, Riverside, they're finding out just how smog is formed. The director of the Air Pollution Research Center is Professor Jim Pitts.
One of the most straightforward and environmentally valid approaches to studying photochemical air pollution, smog, is to trap a parcel of air in some way that we minimize environmental perturbations, for example, wind dispersal, and look at its photochemistry under controlled conditions. This is exactly what we're doing here today. We have two identical Teflon bags filled with specially purified air. We use Teflon because it transmits the sunlight faithfully. Furthermore, it minimizes reactions that occur on the surfaces of these chambers. At the beginning of our run, this whole chamber here is covered by a black canvas to keep it in the dark. In one of these bags, we introduce the pollutant that we're concerned about. And when we want to start the run, we simply pull out the canvas bag and let the sun go to work as it does in the real world. The reaction mixture is pumped from the outdoor chambers into our instrument laboratory, where we measure both gases and particles formed in the photochemical reaction by several types of instrumentation. For example, we measure ozone here by ultraviolet absorption spectroscopy. The NOx, that's the NO and the NO2, is measured down here by chemiluminescence techniques. And the particles, which are also formed in photochemical smog, are measured by a light scattering device over here. But in addition to measuring the rate of formation of products, we always want to measure the rate of loss of the reactants. We do this by gas chromatography.
Even here in Southern California, the sun doesn't shine all the time. So, at the research center, they've also developed an indoor smog chamber with artificial lighting. The material of the indoor chamber is the same as that outside, Teflon. But in this case, the source of light is a bank of high-intensity fluorescent tubes. Most of the radiation from these lamps is in the near ultraviolet region, between 300 and 400 nanometers, sometimes called the actinic ultraviolet. That's the part of the spectrum largely responsible for the production of photochemical smog. In addition to the usual monitoring instruments, the indoor chamber is also equipped with a Fourier transform infrared spectrometer. FTIR spectroscopy is capable of very high resolution, so that individual compounds in a mixture can be identified. In addition, the spectrum is scanned very quickly, in as little as 45 seconds. But to make the system sufficiently sensitive for smog studies requires an additional feature, much longer path lengths than normal.
Now, the long path length aspect of the system is very interesting. As you know, we're working with concentrations in the very dilute range, part per million to part per billion range. And therefore, we need long optical paths. To achieve this, we have a mirror system here that enables our infrared beam to bounce back and forth, 24 meters, 48 meters, up to perhaps 80 meters path length, which gives us great sensitivity. Since we can't see infrared, we're using a small laser beam for the lineup here. We're able to adjust our path length by adjusting this mirror here. Each dot corresponds to 8 meters of path length. And now you see we have a number of additional dots, so we have a longer path.
This system, then, enables a high-resolution infrared spectrum to be obtained of the various products formed in the chamber. The location of these peaks in the spectrum clearly indicates that they're due to nitric acid, and the height of the peaks tells us how much there is in the mixture.
The two chambers that we've been discussing have several obvious advantages. They're inexpensive, relatively so, and when the walls get dirty, we simply throw the Teflon bags away. But they suffer from two major disadvantages. First of all, they can only be run at ambient temperatures and pressures. The other big disadvantage occurs in our indoor chamber, this one here. The fluorescent lights that we use do not faithfully reproduce the true sun. To overcome these difficulties, we've developed a combined solar simulator and smog chamber facility. The heart of the solar simulator facility is this 24,000 watt high-pressure xenon lamp. This lamp produces a true sun in deep space. Now, in the system here, we have Pyrex filters that act just as the ozonosphere does, cuts out the ultraviolet and produces a true solar spectrum at any particular elevation we would like in the troposphere. The mirror system here is quite simple. We have light coming from the lamp, focused on a small mirror here, reflected into the large mirror, and then filling the chamber. The light enters the chamber through thick quartz windows, and the metal chamber itself is really quite large, 1.5 meters in diameter and about 4 meters long. The facility allows both temperature and pressure to be varied over a wide range. As with the other two chambers, the inside of this one is coated with Teflon, and for the same reason, to minimize wall reactions. Now, the data that we collect from our smog chamber runs are fed into a computer and then subsequently plotted out in graphical form as we have here. For example, these are a series of time concentration profiles. Time on this axis, concentrations on this axis. In this particular experiment, we had a mixture of hydrocarbons, oxides of nitrogen, and actinic ultraviolet light. For example, we start with nitric oxide at this level. We see that as soon as we turn the lights on in that chamber, it starts to drop off very rapidly. Concurrently, we see a buildup in NO2, nitrogen dioxide, which has a peak here. Finally, notice that when the NO is just about gone, here comes ozone, and we have an ozone maximum of approximately 0.5 part per million.
The aim of the smog chamber studies is to use simulated atmospheres to find out what smog is and how it's formed. The next step is to see if the same products are formed in the real atmosphere. Well, the same technique of Fourier transform infrared spectroscopy used indoors can also be used outside, though usually longer path lengths are involved, of up to 1 kilometer or so. Another method is ultraviolet absorption spectroscopy. And for that, we need a powerful light source. Like this, a 1 kilowatt xenon arc lamp pointing in that direction. The beam's shining from left to right. It's parallel and doesn't spread out like an ordinary light beam. The light's pointing at a mobile laboratory, parked over a kilometre away. Because the system's mobile, measurements can be taken at a wide variety of locations. The light shines through the back of the van onto a concave mirror, which concentrates the beam before it passes into the UV absorption spectrometer. The computer system in the van is used to process the data, and the resulting spectrum is displayed on the screen. For example, this one is nitrous acid. It's only present in high concentrations at night. During the day, it's photolyzed to give hydroxyl radicals, which play an important role in the oxidation of NO to NO2. Studies, such as those at Riverside, have shown that the formation of photochemical smog is not a simple process. It's only by understanding the chemistry behind the smog formation that effective measures can be taken to control and reduce its occurrence.
Here in my car, I feel safest of all. I can lock all my doors. It's the only way to live in cars. Here in my car.
During smog episodes, people are encouraged to share lifts to work. Federal legislation has also been introduced to reduce exhaust emissions from cars and trucks. But the benefit has largely been lost because of the increase in the number of vehicles in Southern California. Smog episodes are unpleasant, and the pollution can have very serious consequences. For example, the effect on plants can be dramatic. These trees show smog damage, even though they're over 100 kilometers downwind of central Los Angeles. Ozone, in particular, produces this characteristic damage to pine trees and many other plants. Crop damage in a state like California, where agriculture is so important, costs millions of dollars a year. More immediately apparent are the effects on people. The symptoms of a bad smog episode are obvious. Nausea, a raw dry throat, pain when you breathe too deeply, runny eyes, and a general lethargy. No wonder warnings broadcast during the smog season are taken seriously. These warnings are given in terms of an index based on ozone levels averaged over 1 hour. Between 0 and 0.2 parts per million, air quality is said to be good. Above 0.2 parts per million, a stage 1 alert is declared. Above 0.35, stage 2, and above 0.5, it's a stage 3 alert. Since the index was devised in 1977, a stage 3 alert has never been declared. Stage 2 is bad enough. At this level, even healthy people are advised to avoid any strenuous activity. Even at the lower levels of a stage 1 alert, schools are obliged to stop physical activities because children are particularly sensitive to such pollution. Every year, the eastern part of the Los Angeles basin experiences anything up to 100 stage 1 alerts. But there's another potential hazard that's more insidious than the harmful effects of gaseous pollutants such as ozone. Smog also contains a lot of solid organic matter in the form of small particles. The concentration of particles in the air is measured using a high-volume air sampler, like this. All it does is simply to draw air through a filter paper like this for, say, 24 hours. The result is this. To find out exactly what's in the organic matter, it first needs to be extracted from the filter paper. This is done under low light levels to avoid any possible photochemical change. It's known that these extracts contain polycyclic aromatic hydrocarbons, which cause cancer in animals. These hydrocarbons can also cause mutations, thought to be a possible mechanism for cancer formation. Their potential to cause mutations is determined by a test called the Ames mutagen assay. A strain of bacteria is used that's particularly susceptible to mutation. Conditions are so arranged that an individual bacterium will only grow to form a colony if mutation occurs. A suspension of the bacteria is mixed with a growth medium, and a known amount of the compound from the filter paper is added. The mixture is then incubated for a couple of days. The resulting number of cell colonies is counted automatically. This is a measure of the compound's ability to cause mutations. Several determinations are made, and the results are stored in a computer for averaging. The end result is a dose-response curve, showing how mutagenic the test compound is. In this case, there's a threshold value below which no mutations occur. But the ability of extracts from smog particles to cause mutations, and hence possibly cancer, has been found to be very much greater than expected from the known mutagenic properties of aromatic hydrocarbons. This has been linked to the formation of much more potent mutagens through oxidation of these hydrocarbons by ozone and nitration by NO2, processes that may occur at much lower levels than those which cause direct effects, potentially a very serious hazard indeed. What's more, smog formation isn't just limited to the Los Angeles basin. Photochemical smog is common in any large city wherever there are lots of cars and plenty of sun. New York, Sydney, Athens, Tokyo, even in London, high ozone levels are recorded during hot summer days. But it's in Los Angeles that photochemical smog was first recognized. Despite efforts to control the pollution by legislation, it's here that smog occurs most often and most seriously. So, if there is an acceptable solution to the problem, it's here in Southern California that it's most likely to be found.
You read my mind here. A couple of minutes after 5 o'clock, this is KFI with Byron and Tanaka and Russ Carlton, who's graciously consented to tell us exactly what to expect when we get our cars aimed out on the streets trying to get home tonight.
It is very heavy all around this afternoon on our freeway system, and the major problem continues to be those two vehicles over the side, southbound San Diego Freeway between Roscoe and Sherman Way. CHP now looking for a disabled vehicle to add to the problems. Ventura Freeway westbound at Balboa. We have 4 vehicles that crashed in the slow lane, Harbor Freeway southbound at Rosecrans. And the southbound side, of course, is very heavy as well. We have 3 vehicles now up on the center divider. Southbound Golden State Freeway transition to the eastbound Ventura. CHP checking that problem. Kids throwing rocks at the cars. CHP and the LAPD checking that report. San Bernardino Freeway westbound at West Boulevard. And on the Golden State Freeway southbound at Western Avenue, an accident now on the center divider. With traffic, Russ Carlton, KF.